an example. Uh, uh, Let us say uh, you are a researcher and you are researching on viruses. You want to see whether you can create a virus, or you want to see whether you can create an antivirus. Okay, let's say you want to create an antivirus. So to create an antivirus, you must create the virus first of all. So you must introduce that virus to the network and then see whether your antivirus is going to work against that virus. Now, let's say you are working at the internet level. Now, you are not going to introduce a virus to the internet because the internet has no owner. We don't know who the owner of the internet is. So there's nobody you are going to ask permission to introduce your virus. There's nobody you are going to tell that I'm researching on antiviruses. So I want to introduce a virus and to see if my antivirus is working. You are not going to do that because there's nobody to ask. And secondly, we have different time zones. Right now, we are in the middle of our work time. But some people are just waking up right now. Now, when night reaches, if it's Kenya, for example, and it's night time, and you say, I'll introduce my virus when people are not working, and this is the internet, there are some people who are just waking up. As we are going to sleep, they are just waking up. So your virus is going to interrupt them. So basically, you are not going to do your experiments on the live internet. There's no owner of the internet who you can ask for permission, and there are different time zones. So supposing you want to continue with it, then you are not going to say, I'm not going to do research. What do? You create a simulator. A simulator, in other words, you create something that imitates the working of the internet. And you try, and it's software based, and it can be loaded on a machine, and you try as much as possible to make it imitate the internet. So this is what virtualization does. So in virtualization, that virtualization layer creates a simulator of the computer hardware. So it simulates the computer hardware, but it's software. Just give me a minute. I'll be doing. Let me address something. Sorry about that. These are some of the hazards of working from home. Okay, so I was talking about virtualization. So in virtualization, what we are doing is that it's software that is created over the hardware system, and it simulates the whole physical system. So what I mean by physical system is that it now simulates the the computer or your PC or a single machine. But remember that it is simulating, just like I've said, you can create a simulator of the internet and you load it onto your machine. Like for networks, we have NS3, which can be used to simulate the internet, and you load it onto the machine, and then you can do experiments on that simulator. So for the computer, we do that, and when we do that, we call it a virtual machine. So, and the concept is simulation, which I've said, it is just software. So a virtual machine is created in contrast to physical machines over the simulation layer and has all the characteristics of a physical system. So 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 under this approach, under the virtual machine approach, application loads are assigned through virtual systems rather than directly to physical systems. Now, remember that a virtual machine, like I've told you now, is software or it's a simulator. You can create many copies of it. So you have one physical computer, but you created a virtual machine. And so you can assign, because I've said in the traditional approach, when an application is used without the virtual machine, that application ties all the physical resources. But now here you've created another layer where you've created the virtual machines. So using those virtual machines, you can create 10 copies, because this is just software. You can create 10 copies of the virtual machine. And using those 10 copies, you can have 10 different applications, each of them attaching to a copy. So those 10 applications won't notice that they are using one physical machine. So that is what virtual machines do. So virtual machines decouple software applications from hardware. In other words, when the software is running, you are not tying resources, because the software is accessing the resources via a virtual machine. So such decoupling makes it easier to map and demap tasks to resources. So virtualization brought the true essence in scaling capability of distributed systems, because loads could be shifted to other and stronger sets of resources without disrupting service. This provides opportunity for real-time system scaling. So like I said earlier on, most times we use a very small percentage of our computers. Now you find somebody is buying a high-end computer and he's only using 1% of it. 99% is not being used. Now, in the grid computing, in fact, one of the things which advanced the grid computing concept is that as long as you attach to the grid, which is basically a network of computers, all are running virtual machines. What happens is that via the concept of virtualization, then as long as somebody is attached to the computer, somebody else can use his compute power because they are accessing his resources via virtual machines, meaning that no single software application is tying those resources. So such systems with such characteristics are known as scalable systems, where definition of scalability is the ability of a system to accommodate growth. Ability of a system to accommodate growth simply means that when more users require resources, the users who are already using the resources will not even notice that 10 additional people have come in and they are sharing those resources. So then virtualization coupled with this resource pooling introduced more force and flexibility in the systems. So resource pooling simply means that as long as you've decided I'm joining the grid, yeah, it means that you are adding your resource to the grid. And of course, to join the grid, then you have to put that additional layer onto your computer. So if you don't put that additional layer, then you have not joined the grid because you have not agreed. You've not agreed to pool your resource in the pool. Now, this is just one of the shortcomings of grid computing, because what it required is not something that is like plug and play. It required you to load software that enabled grid computing. So without that software for grid computing, you could not join the grid. Now, and that was a technical exercise which not every Tom, Dick, and Harry could do. And that is one of the things which made grid computing not possible. So hardware virtualization allows dynamic resource addition into the system. Now, just like I said, all you need to do is to add that additional layer of software, then link your computer onto the internet, and you have joined the grid. So it created opportunities for developing systems that can grow as per business requirements. Now, this also led to advancements with advancements in internet technology. Communication over the web also started showing its strength. So internet technology, we had bigger internet speeds. The web also changed in its features. So this is what virtually improved developments in grid computing. So alongside that, every time we talk about the internet, then we must talk about the web. Now, remember, the internet was created to share documents. The web was created, the internet was created to share information. Now, the web was created to share documents. Now, the web was created in CERN laboratories in Switzerland. There was a scientist working there, and he wanted a way of sharing documents. And you see, the scientific community basically just share facts. So their documents are usually textual in nature. So this scientist wanted a faster way of disseminating scientific information, which most of the time is data and graphs. So he came up with the HTTP and HTML. So that was the basis of the web. So the web, basically, the World Wide Web is basically a network of documents. But the World Wide Web is dependent on the internet. Internet is just used to share information, but www was used to share documents. So it was now called the web. So the web involves what is called collaboration. Now, in collaboration, multiple users simultaneously work on the same venture. And this is what the scientists really wanted, because he needed collaboration. That laboratory, the Sun Laboratory in Switzerland, is a highly advanced laboratory. So he needed input and output to scientists around the world. And sometimes this information, you need it to be done in a fast way. So the web was created to enable collaboration, and like I've said, the World Wide Web is a network of documents. So this collaboration was always a desire from the early days of computing. So without the collaboration capability, it would not have been possible to develop a relatively large computing system spread across wide geographic locations. So the web is as wide as the internet is. So the web needs the internet. But in the web, what you do is that you're using the internet to share documents. But those documents are interlinked together. If once you have the URL, or once you embed a URL into your web page, then you find that your web page is going to be connected to another document via that URL. This other document has a URL to another document, and so on. And that's why I'm saying the web is a network of documents. So distributed computing provided the scope where processes could collaborate with each other. And then web services played the primary role, where web applications would enable different users from different geographic locations to collaborate in real time. So then we have what are called web service standards. So, like I've said, the web was created in the Sun Laboratory, and basically the basic web was made up of HTML, HTTP, URLs. So those are terms associated with the web. Now, those are standards. Once scientists were sharing documents, the business community saw an opportunity there to advance their business needs. So they demanded more. They said, okay, why is this thing only limited to the scientific and research community and academic community? Isn't it also possible to use it for business cases? So, but you see, the original web standards were serving the scientific and research community relatively well, because their documents don't have too many things. Now, but the business community, their documents would require more things. They would require animations, they would require graphics, they may require sound, and so on. So the web standards had to be enhanced. And this is what we are referring to, the emergence of advanced web service standards made software integration become effortless. So these standards, because like I've told you, the business community required more of their documents. Now, for these documents to have things like animations and so on, they needed to access other software through APIs. And this is what we mean by software integration. So you are running a web page, but you want this web page to do other things. So these other things may require software. So that means that different software have to work together. So this is a so software integration became very important. So developments in the field in web service standards led to development in the field. This made it possible to glue together applications running on different platforms and combine data from various sources. So the two major developments in web service standards was the Web 2 and what is called mashup. So we had the Web 2 standards, and then we had what is called the mashup. So we look at each in turn. Web 2 is the second generation in the development of the World Wide Web and appeared after 2002. Earlier technology of web was more static in its approach, although some collaboration capabilities were present in Web 1 as well. So Web 1 was static. There was a document, and this document was mainly textual. And this document could embed in it URL so that you could get other documents. But there could be some collaboration. There was a way you could write in Web 1, there was a way you could write a document that you made collaboration, but still the document is fairly static. You don't see a lot of animations and things like that. But you could do some collaboration, like there's what is called request for comment. These documents are used by the internet, people on the internet, to share ideas with each other. And it's possible to add on to that document. It is static. I mean, you add on to it, and the person at the other end will see it. But it's not real time. In other words, you'll write a paragraph. The other person cannot really respond to that paragraph. He can see the paragraph. He can see that the document has been edited, but it is not real time. He cannot respond to it immediately. He can only add to what you have written. That is what the collaboration in Web 1 was able to do. But Web 2 enables collaboration by allowing sharing of user-generated content. Now, for example, in social networking, which you all use now, blogs, photo and video sharing sites, etc. So in Web 2, you write in a blog, you will write a question. You can state a question, and within minutes, you'll find 100 people are responding to your question. So this is because of developments of new developments in the web standards. Then, so we have said the major advancements in web service standards were Web 2 and then mashup. So then we have what is called mashup, which is a web application that can combine data from multiple web sources into a single interface. Now, mashup, the literal meaning is a mixture or fusion of disparate or heterogeneous elements. So the name mashup in web technology is derived from this idea. So one application of service may serve multiple functionalities. So the idea behind mashup was to mash the best available web applications together effortlessly into a single application for the convenience of users, done by calling those applications using their open APIs, application program interface. For example, Google Map in web application. Now, Google Map is an application, but you could be writing to somebody or inviting somebody to your home So you write the invitation, and under the invitation, you could call, you could have a link to Google Map. So what will happen is that he's reading the text, and then when you tell him the direction is as shown here, he clicks on here and Google Map appears. So that is what we mean by mashup. So Google Map in this case can be integrated into any web application through the application program interfaces. So that is Web 2. Now again, you can notice that Web 2 is very independent from virtualization. They are not related so far up to this moment. So after that, there also came another concept, what is called the service-oriented architecture. So in service-oriented architecture, rather than somebody purchasing software, somebody is purchasing the service that that software is giving. So in all the developments in the field of computing, communication, and web, in all the developments in the field of computing, communication and web services led to the need for a more modular and flexible approach to IT systems. So you can see we've talked about communication developments in the computing, and we've talked about developments in communication, and now we've also talked about communication about web services. So all this meant that we need things to be modular, because if you look at mashup, you are talking to somebody, you are using text, or you are using an application to create a web page, or you are using an email to create a message to somebody, but you are now calling the Google Maps, different softwares. So it needed software to be independent of each other. So software systems were difficult to build without language independency and loose coupling approach. So in other words, what we are saying now, that you could create a big application from many different modules via their APIs. Now, for this to happen, there needed to be language independency. So users don't need to ask which language are you using or which platform are you using. So you don't need to know whether somebody is using Java, C++, or whatever. And you don't need to know whether somebody is using Unix, Linux, Microsoft, Apple. You don't care about that platform. So this is what led to the emergence of what is called the service-oriented concept in application or software system development. So software-oriented architecture is more a methodology than a technical approach. It relies on developing application components as software services as its fundamental principle. So instead of talking of an application, or rather loading an application onto your computer, you will just look for that service. For example, in Google Maps, the service you are looking for is the service for location. So you are looking for a service called location. If you wanted to include maths, a calculator, you are calling that calculation service. So this required software to be modular, and that's what we are talking about: software service-oriented architecture. So rather than asking for applications, you are asking for the services offered by that application. So what are services? Services are independent entities. They communicate via message passing. They use standardized interfaces and can be developed based on platform as well as in a language independent way. Since systems can be developed by integrating services in the SOA paradigm, they remain flexible to changes. This dynamism fits well with the need of ever-changing business and is considered as an essential foundation of cloud computing. So the moment the service-oriented architecture was conceived and implemented, then cloud computing became possible. Now, again, you can see the service-oriented architecture has no relation whatsoever with something like virtualization. So service-oriented architecture describes the philosophy behind how large development projects are organized through divide and conquer and communicate approach. So what happens is, instead of creating one huge application and insisting on somebody using that application, you create small components. So let's say you create 10 components. Somebody will come and use 3 components to create his specific application. Another one will come and use 5 components to create their applications. But remember, these components are software. So they are reusable components. So code in service-oriented architecture, code is developed in reusable modules that can talk to each other. It encapsulates design decisions that may change in the future. In other words, you can change a component. Now, when you change that component, anybody who is using that component will take advantage of the new changes that you have made. So you only need to make change to one module, and that change is reflected to several people who are using that module. So it ensures code, service-oriented architecture ensures code modules can be combined in different ways depending on specific software deployment needs. That is what I was saying. Somebody has created 10 components. I only need 3, so I'll combine those 3, and I'll have an application that is very specific to me. Somebody else needs 5 components. He's going to take those 5 components. Now, of those 5 components, one is being used by the first user, but the second user also needs it. He's going to reuse that component and is going to create an application that is specific to him. So service-oriented architecture draws from fundamental object-oriented software design principles. I'm sure you've done object-oriented design, and you know that in object-oriented design, we create software from modules which we refer to as objects. And we know that objects are independent units. They have their data structure, and they have their code. So somebody known as Harriet Freiman came up with 7 principles for software-oriented architecture. One, he said, principle one is that they are open and standards-based. In other words, they allow interoperability. So under SOA, any application you develop must be subject to standards. And these standards should be visible to everybody. So as long as somebody is following those standards, whatever application they create, it's going to be usable by other people. It is platform neutral, meaning that it's encapsulated, so a service works identically on Linux or Windows. It doesn't matter. In other words, it doesn't matter on the platform. It's location transparent. It should not change based on user location or location in the global infrastructure. In other words, it's location transparent. It's peer-to-peer. There should be no primary or secondary. There should be no primary or secondary service. Every service created is equal. This means that services can spawn and scale out without a single point of failure. Loosely coupled, this can enhance capability within a service without impacting another service. It's interface-based. Each service is opaque. Now, opaque simply means all you need is the API. You don't need to know the details of the workings of that application. All you need to know is the entry point and the exit point. Is costly grained. It must operate at a business level, not down in the bits and the bytes. This makes it more reusable. So somebody doesn't need to know the intricate programming details. So a software-oriented architecture paradigm was created using extensive markup language, the web service description language, the simple object access protocol, and the universal description, discovery, and integration. So in SOA, the set of services are defined with known and described interfaces which can communicate with each other. The service interfaces are specified in XML, and the services are expressed in WSDL. Now, this form topics under the internet architecture. So I don't think I want to go into this, but I would like you to go and read a bit more about these three. These are the things that are used to create the SOA paradigm. Then we have utility computing. Now, again, utility computing was borrowed from electrical power distribution, where you ask for a service and you pay for it. So remember, once you connect to the electric grid, you pay depending on what you are doing. If you decide to have a workshop and you have a welding machine, obviously you're going to pay more. So in computing, people said, okay, now that we have linked computers, now that we are talking about compute resources, then why don't we charge people according to their usage? So when this concept came about, then the term utility computing came about. So utility computing has the following characteristics. It's a scalable computing infrastructure. In other words, it's made up of heterogeneous resources that can be grown as much as required in real time. In other words, the resources are diverse, and the number of people can grow or it can dwindle, but the people on that network will not know. Now it's a single distributed computing environment spread across the globe. So utility computing, the network is global. And this is possible these days because of the high-speed network. Collaborative, work facility from different locations. So you can find people in different countries are working on a project in real time. So this is empowered by modern age web service standards and a flexible application architecture, which is easily modifiable, or rather its description is that it's easily modifiable with changing business requirements, empowered by the SOA paradigm. So all the features of utility computing combined with virtualization has created a scope for a new avenue for computing. So you can see I've been walking you through various technologies. Now they each are developing independently, and yet they seem to be now converging. So under this new model, vendors could arrange all required computing facilities which users could consume on a payment basis, what I was saying. Payment is calculated on a use basis, and users need not take responsibility of system management. So under utility computing, you are just paying for a service. You don't care where the hardware comes from. You don't care about the management. You don't care about the upgrade. What you are doing, you are just paying for a service. Now, this provided a huge benefit from users' point of view. So this model of computing is known as utility computing. The idea of such a model was first presented by John McCarthy, a professor at MIT in 1961, which showed that computing can be delivered as a utility service, much like electricity. I think we mentioned this yesterday. The only thing that we are adding here is that we've introduced the aspect of payment. So this model, the utility computing model, has two important features. The service is available on demand, and the use basis mode of payment. You only pay for what you have used. So in this model, computing owner or vendors own, build, and manage the computing resources and infrastructure. And then they deliver any kind of computing facilities that the customers can access as and when required on a rental or metered basis. So the utility computing model enabled small business owners to afford high performance computing facilities, which with their limited budget, they could never dream of. Now you see, when computational needs are offered as services, then you pay for them as a service. So you don't need to buy certain hardware, you don't need to buy all the software, and probably it's because you may be using them on an one-time basis. Like for example, the Google Maps. How many times do you use it? But you'll find that you may want to show somebody direction, and it's only at that time that you need to access it. So that service, that is offered as a service. Now, of course, Google Maps is a software, but this software is giving a service. So what you are doing is that you don't have to purchase the software. You only have to purchase the service. So then we have the concept of what is called autonomic computing. So which utility services were generally built to serve a large number of customers. So the utility computing idea meant that service providers would have to arrange and manage a huge computing infrastructure. So under utility computing, things are offered as services. So, and users request and pay on a needs basis. And we have, and we've said that the web services are global. So you can imagine globally where different people are asking for different services. So this is huge. So what happens is that with system growth, more human interventions are required to manage the increasing number of hardware as well as to monitor the software issues. More human intervention means increasing the possibility of human errors. So because users are just requesting for services, and this network infrastructure is so big, it means that will require a lot of human interventions. But now this is not possible because these services are in different places. So manual management of such a massive setup was not a viable idea. So a new concept known as autonomic computing was first presented by IBM in 2001. Now, autonomic computing, now you'll notice, or you should have noticed by now, that advancements in technology borrow from various areas. So autonomic computing borrowed from the human nervous system, where the human nervous system controls various physiological activities like breathing, sensing, etc., without conscious intervention. When you wake up in the morning, you just wake up and go about your you go about your duties. You don't care about am I breathing properly? How is my heart rate? And so on. You don't really care about that unless something is not working very well. If you're struggling in breathing, you will care about that. So things are controlled from somewhere autonomously. So the ability of an intelligent computing system to manage itself without any human intervention is what is called autonomic computing. So these systems can reconfigure themselves automatically with changing conditions and protect themselves from any technical failure. So autonomic computing, the term came from the word autonomy, where autonomy is the capacity of a system to take its own decisions about its actions. Now, the development of autonomic computing was made possible through application of artificial intelligence concepts. These days, artificial intelligence is a hot topic. If you remember, the chancellor came up, challenged the school to come up with an AI program, which we did 3 weeks ago. If you remember, we were not around, so we were coming up with a master's, an MSc in AI. AI is now the real thing. Initially, AI was hype, and AI you found people dealing with discrete components. You find somebody dealing with neural networks, another one with the expert systems, another one with the machine vision, and they were dealing with these things. Those they are part of AI, but they were dealing with them as separate entities. Now, what happened and why it has picked up, and again, this is just technology, is that people are developing small apps that are independent and are doing independent things. So why AI has picked up is that people are picking these small components which which are self-contained, and they are putting them together, and these things are working together and doing considerable things, and that's why AI has picked. I mean, the concept of AI was there, but AI was being treated as very discrete components. But now, and I believe it also has to do with the software-oriented architecture. With the software-oriented architecture paradigm, you find, and I've seen a lot of young people like you, this is what they are doing. They're developing systems which are doing amazing things. And what they're doing, some of them are not even good programmers. They're picking different components and putting them together based on a customer's needs. And something is working. So in autonomic computing, systems are controlled through predefined policies and rules to avoid external intervention. Runtime decisions are taken based on policies and the knowledge base of the system in response to collected units, collected inputs. So IBM conceptualized the idea of autonomic computing, and they defined 4 areas of automatic computing as shown in the figure. So autonomic computing infrastructure is made up of self-configuration, self-healing, self-optimization, self-protection. Self-configuration is the ability to configure a system based on requirements without any external intervention. Self-healing is the capability of discovering, diagnosing, and correcting errors. Self-optimization is the ability of a system to automatically control resources for optimal utilization while producing outcome in a timely manner with changing business scenarios. Self-protection is the capability to identify any occurrence of hostile behavior and take corrective action to make the system less vulnerable. Now, what is self-behavior? There's hostile behavior, this last one. Hostile behavior includes virus infection, the denial of service attack, and then unauthorized access. So autonomic computing is able to take care of this, of security and privacy related issues. It has played a very important role in developing cloud computing systems, as resource management at cloud data centers is absolutely governed by this model. So autonomic computing proposed by IBM. Now in cloud computing, it's implemented by agents. Now remember, software agents are pieces of software that you configure and you send to do tasks on your behalf. Now, because they are pieces of software, they travel over the internet, they go to a location, and they do certain tasks depending on how you have configured them. So software agents are the ones which have been used in cloud computing, which have been used to implement autonomic computing. Now, having reached there, we know all those things, they are separate. They were being developed with different objectives, but with the time, they have now converged to come up with the concept of cloud computing. So the invention of the grid computing concept, which I talked about earlier, was a major step towards the future age of computing. The major advantage of cloud is its capability of time scaling. Unlike grids, computing resources in cloud can be added in real time to meet demand of computing. Now, actually, cloud computing is the simple, implementable version of grid computing. Now, grid computing basically dealt with the computational aspects. In other words, sharing the computational resources. In other words, if you had a computational challenge, your computer is not powerful enough to run your simulation, then you use the grid so that your simulation can run. Because in the grid, you are going to draw your compute power from a shared resource. And I said that to join the grid, you must run the grid software on your computer. So without the grid software, then you can't. Now, the grid software was quite complex. Now, cloud computing was a simplified version, because in this case, we are now just talking of services. You are accessing services and not necessarily compute power. So cloud computing was made possible by resource virtualization, restricting or decoupling applications from direct access to physical resources. So cloud computing is the delivery of distributed or grid computing power based on the utility service model generated from the autonomic computing infrastructure, introducing the new era of computing known as cloud computing. So you can see here we are talking about the grid, we are talking about utility, we are talking about the autonomic computing. So the step-by-step development of development towards cloud computing era from the early age of computing is as shown. Now, this diagram, you will blow it up. This diagram is basically showing all that I've been talking about. Mainframe, client server systems, personal computer, peer-to-peer computing, distributed computing, cluster computing, grid computing, resource virtualization, advanced web services, software-oriented architecture, utility services model, autonomic computing, and finally, cloud computing. And these are brief summaries of the functionality of each of these things which I've been talking about. So cloud computing evolution has been an outcome based purely on technological advancements in different fields of computing. What I've already mentioned. Developments in the fields like computing, hardware, distributed computing, communication technology, web technology, application architecture have equally contributed to the process. The next figure summarizes how different technologies have been combined and contributed to the emergence of cloud computing. So again, cloud computing is as a result of convergence. Now, each of these technologies was developing independently, but they are now combined and they have formed what is called cloud computing. So this is the history You can read this. So in cloud computing, it's not about that. The resource virtualization has enabled decoupling of software systems from physical hardware devices. Computing systems accessed by users have become portable over other sets of hardware devices. This makes the system more tolerant and puts a stop to the resource shortage problem, as the decoupling feature provides scope for adding more resources to the resource pool. Such kinds of systems that can grow as per requirements are known as scalable systems. And that brings us to the end of that lecture. Any questions or any comments? So we've ended up with cloud computing. Now, the next thing, I gave you an overview of cloud computing. I've given you the historical concept, the historical context, and the various technologies that have contributed into cloud computing. Now, next, we shall now be looking at what is this cloud computing? Now that the technology is there, what is it? So we shall now go deep into cloud computing. Now, I had suggested that we have a makeup class. I received email that you are not interested in this makeup class. And I don't know why. You know, when I was a student, when I was like you many years ago, I did physics. Physics can be quite, it can be quite hard, and the mathematics can be awesome. I actually did maths and physics. It can be awesome. So there are lectures that half the time I didn't understand what the lecturer or the professor was talking about. But I attended the class. I didn't understand. Sometimes in the afternoon, you want to doze off. But I attended, and I'm just talking about me. I'm not talking about you. Some people, I would see some people asking questions, and I would ask myself, you mean this guy is following what this man is talking about? Like in physics, there was something called Schrodinger equations or quantum physics, highly mathematical. So you don't follow. But what I noticed, at least that's for myself, if I missed that lecture, and most of the time I didn't understand what this guy was talking about, I would never get that concept. If I missed it. If I understood it, later on when I'm reading on my own, I would get what he was talking about. So I concluded that attending lectures, sometimes your brain has what is called the subconscious. So maybe my subconscious was capturing those things. Because if I miss that lecture totally, I would never understand. I would never understand it. Even though when I attend physically, I will never get what the guy is talking about. So basically, that's why we come to teach. Otherwise, I have the notes actually. I have all the notes. I could just post them and ask you to read the notes. Maybe that's what some of you want. I have the notes up to the end of the semester. But sometimes it's good, just like I've tried to explain, for the lecturer to talk, whether he's mumbling or whatever it is. Sometimes it's just good to be there. Your subconscious is going to get those things. So based on that, I'm still available. I don't want to come on Monday afternoon, and find an empty class. So you will still reconfirm to me whether you still need that makeup or you don't need it. I think I'll end my presentation there. So let's talk.